I love you, baby. Okay. Good morning, gang. So today we're going to talk a little bit more about improper integrals. And we're going to move from the computational side of things more towards like addressing the question of convergence through theorems, which is exciting because that's the spirit of where we're going. A little bit more concrete about what I mean by that. Let's see, some other pens here. That's an interesting color. Oh, that's a dead refill. There we go. All right, so I flip on the Zopcam and I will show you what I mean. So the first thing we're going to do today is address some more complicated improper integrals. You've seen type 1 integrals and you've seen type 2 integrals, but you haven't seen what happens when I mix them together. And that can be worth looking at. It certainly is something which happens. So we got to play with it. The other things that I want to do, and the kind of more important things, is develop some theorems on convergence of improper integrals. And that's going to allow us to look at these things from a slightly more sophisticated perspective. And most importantly, it's going to serve as a gentle introduction to the type of thing that we'll be doing for the next few weeks before exam 2. I remember the word theorem is just a math lingo term for important true statement. True statement that deserves a little discussion of proof, like why it's true, and that you refer back to often enough that you want to give it a special name. So a fact is a true statement that you use once. A lemma is a true statement that you use 2 or 3 times, and a theorem is a true statement that you find yourself using all the time. Paul Helmusch has a cute joke about that if you want to Google it, but I won't burn any more time on it. So the first thing I want to address here is how to handle integrals of the form negative infinity to positive infinity f of x dx. You might call these bilateral integrals because they go off to infinity in both directions. So bi and lateral, both directions, or 2 directions. And there's several ways to interpret them. Neither is incorrect, but only one of them is what we use in this class. So one of the things that you'll learn about mathematics as you proceed higher and higher and higher in the math world is that well, 1 plus 1 is always 2, and there aren't a whole lot of other ways to think about that. There are other ways to think about it. And the same is true of this integral, right? So there are valid ways of doing things that conflict with each other sometimes. And it depends on your set of axioms, your basis for reasoning, or the space in which you're working. So to look at how we should handle these, I want you to consider the integral from negative infinity to infinity of x dx. Of course, you know what the graph y equals x looks like. So the integral from 0 to infinity of x dx would be measuring all of this area. Oh, I'm sorry, my pen smudged. And the integral from negative infinity to 0 would be measuring all of this area, right? Here's your y-axis, here's your x-axis. On the one hand, the area being measured from negative infinity to infinity, if you allow this to go all the way out, is clearly infinite, right? Can everybody see that? Like if I just look at this area and I let it go all the way out here, I have a triangle whose base is infinite and whose height is infinite. Definitely not a finite area. And the same is true on the left-hand side. You know, if I let this go all the way out, then that's a triangle whose base is infinite and whose height is infinite. But it happens to be the case that if you do things symmetrically, like I integrate from negative 10 to 10, that would be 0. If I integrate from negative 20 to 20, that would be 0. If I always think of this as expanding symmetrically, then the integral would always be 0. So should I call this integral 0 and convergent, or should I call the integral divergent? That's the question. Does anybody have an opinion on this they'd like to share? I'll open up the chat if you want to type something, and let's do a little vote here real quick. So first, any questions on what I'm asking you? Is it clear why there's an issue here, why there's room for misinterpretation? Are there any questions about what this integral represents or what it is I'm trying to ask you? Remember, you can hold the spacebar to talk, or you can type in chat. Okay, then, hands up if this should be a convergent integral, because, you know, the symmetry, these balancing each other out and always coming out to 0. You can use the react button there to give a thumbs up if you think this should be a convergent integral. Again, neither answer is wrong. I'm just curious how you guys feel. Zach, yeah? Anybody else of the opinion that due to the symmetry, this is an odd function and I'm integrating over a region that is symmetric about 0. So those integrals are always 0, right, according to Calc 1. Certainly it makes sense geometrically that they balance. Hands up if this should be a divergent integral. Give me a thumbs up if this integral should diverge. Todd, okay. So both are totally valid. In this class, we're going to pick one perspective and take it. And I'll show you exactly what I mean, and I'll give you a rule so that you're never ever confused about this. I'll tell you right now that I'm in the first camp, right? I think this is a convergent integral in my book, because one interpretation is that this integral is the limit as r goes to infinity, integral negative r to r of x dx. And then without the limit, each of these integrals is 0. So this is the limit as r goes to infinity of 0, which is 0. And for the most part, when I've needed to use these sort of things, this has been the interpretation that has borne the most fruit. Meaning when you're looking at a physics application or when you're trying to look at a number theory application, this is the way of interpreting a bilateral integral that has been the most useful in terms of developing results. So I'm in the same camp as Zach Hull. However, our book's interpretation and this class's is the one that Todd gives. This is a divergent integral according to our book because we need to treat it as the limit r goes to plus infinity, limit s goes to negative infinity, integral s to r x dx, and split it up. As the integral from s to 0 of x dx plus integral 0 to r of x dx. And sorry, I got a little bit short on space there. Both of these are totally valid. There's nothing wrong with either one. But the ethos that our book carries, kind of the way of thinking that our book runs is if the area is infinite, then the integral diverges. And here, yeah, undeniably, the area is infinite. Another way of saying this is if any part of the integral diverges, then the whole integral diverges. And this is the way of thinking that you should follow when you're dealing with all of the homework problems that involve a mixture of type 1 and type 2 things, or a type 1 integral that is bilateral, or anything like that. In other words, to begin this problem, so an official solution to this problem would look like this. You begin by taking your integral from negative infinity to infinity of x dx, and you split it up. Doesn't matter where. I think splitting it up at 0 makes the most sense. So I'd say treat this as the integral from negative infinity to 0 of x dx plus the integral from 0 to infinity of x dx. And then each of these is a type 1 integral that we already know how to handle. Each of these is the sort of thing we were looking at on Wednesday. So then I would write this as lim r to negative infinity integral r to 0 of x dx plus lim s to positive infinity integral 0 to s of x dx. I'll continue this down here. that would be lim r to infinity. Well, the integral of x is x squared over 2. And if I evaluate that between 0 and r, I'll get negative r squared over 2. I'll write it as 0 minus r squared over 2 plus lim s to positive infinity s squared over 2 minus 0. And since both of these come out to be infinite, let's see. This would be infinity, negative infinity plus infinity. And while it's true that this is an indeterminate form, right? Infinity plus infinity is an indeterminate form. We would conclude that the integral diverges because if any part of the integral diverges, the whole integral diverges. Right, and if you wanted to be extra verbose about it, you could say here, clearly, the integral from 0 to infinity of x dx diverges. Thus, integral negative infinity to infinity x dx is divergent. Okay. So those symmetry arguments, they're nice. But for us, the way we handle a bilateral integral is by splitting it into two one-sided integrals. And then if either of those one-sided integrals diverge, the whole integral diverges. I know that this can be a little bit hard to wrap your head all the way around, so I'd like to take a second and answer any questions you may have developed while we were talking about this. Okay. So let's try another bilateral integral. Actually, yeah, why not? All right. Any thoughts on how I would start this problem? Come on, focus. Focus, focus. There we go. All right, someone help me out. How do I get started here? Long before u sub, I've got some other stuff I need to do. This is an improper integral. You're right that u sub is going to be the trick we use for an antiderivative. But before we can do any antiderivative work, we need to remember that this integral is improper. It's not a Riemann integral. So it needs all that sort of special treatment that we introduced on Wednesday, the same sort of stuff I was just doing down there a minute ago. Yeah, I need to express it as a limit of finite integrals. Even before that, there's something I need to do. Think about what we just learned, what we just introduced. This is a bilateral integral going from negative infinity to infinity. So there's a problem at both endpoints, right? Negative infinity all the way up to positive infinity. So I need to do something before I can even put in the limits. There's one other thing. What did we do on this last problem? What did we say? Good, yes, we need to split it up, right? Remember, our way of interpreting bilateral integrals is always to split them up. You don't have to split them up at 0, but that's what I'm going to do, and oftentimes that's the most reasonable thing to do. I could have also split it up at 1. I could say integral negative infinity to 1 plus integral 1 to infinity, but 0 is right in the middle there, so it's kind of nice. And it's also a nice number to evaluate at the end. So first I express this as a sum of two one-sided integrals. And then each of those get their own limit, right? And it has to be with different variables. I can't use the variable r for both of these. I have to use a different variable for each. And that's kind of the lesson from the example we just played around with. So this is limit, I'll say r to negative infinity, integral r to 0, x e to the negative x squared dx, plus limit s to positive infinity, integral 0 to s, x e to the negative x squared dx. And then yes, in each of these, I do a little substitution. So in the first fellow, I might let u equal negative, actually, I'll just say u equals x squared. And du equals 2x dx. The lower bound r goes to r squared. And the upper bound 0 stays 0. Here I'm going to make the same substitution, but I'm going to say z equals x squared, and dz is 2x dx. And now the lower bound 0 goes to 0, and the upper bound s goes to s squared. We've seen this sort of thing before, where you're making the same substitution in two different integrals for similar reasons to using r and s instead of like r in both of them. I'm going to use u and z instead of z in both of them. Okay. So the differential in each is 2x dx, so a 1/2 will pop out of each. So here I'll have limit r to infinity, 1/2 integral r squared to 0, e to the negative u du, plus lim s to infinity, 1/2 integral 0 to s squared e to the negative u du. I'm sorry, e to the negative z. Shit, I did the thing. E to the negative z dz. All right, okay. One of these integrals converges, and one of them diverges. And if you think about the graphs, you can spot which one is divergent right now. One of these is kind of, I would be tempted to say, obviously divergent. Can anybody spot the obviously divergent integral? Oh, wait, no, hang on. I might have to eat those words. Yeah, because of the square, these guys might both converge. So let's go ahead and just do the computation. I can pop this 1/2 out past the limit, and I'll have limit r to infinity, negative e to the negative u, evaluated from r squared to 0, plus 1/2 limit s to infinity, negative e to the negative z, from 0 to r squared, or from 0 to s squared. And now if I plug in my upper and lower limits here, upper and lower bounds, I get 1/2 lim r to negative infinity, sorry. Must be one of these Friday mornings. So my limit in the first integral r is going to negative infinity. I think I left my negatives off. So here's r negative infinity. When I plug in my upper bound here, I'll have negative e to the negative 0. That's negative 1. And then I subtract what I get when I plug in my upper bound, which is negative e to the negative r squared. And then plus 1/2 limit s goes to positive infinity, negative e to the negative s squared minus negative 1. Okay. So yeah, we had to start by splitting the integral. That's important. All right, if you have an integral from negative infinity to infinity, you always need to begin by splitting it. Then each of those integrals is a regular type 1 integral. And the only thing you got to be careful about is making sure you use separate variables for them. So I use r in the first integral, and I have limit r to negative infinity, integral negative r to 0, plus limit s to positive infinity, integral 0 to s. So this is the integral from 0 to positive infinity, and this is the integral from negative infinity to 0. And when you add those up, you get the integral from negative infinity to infinity. Each one got their own little u sub. And then once we do the u sub and take an antiderivative, we get to this evaluation step. So now we need to take the limit as r goes to negative infinity in this expression. Any thoughts? As r goes to negative infinity, what does negative e to the negative r squared do? We can kind of plug in infinity if you like, or plug in negative infinity. This minus minus here makes plus, and I'll have e to the negative of negative infinity squared, like this. And I can think of it similarly in the second piece. This is negative e to the negative of positive infinity squared plus 1. It's true. Yeah, that's one way to think about it. The fact that this exponent here is negative means that this is 1 over e to the parentheses negative infinity squared. And we could treat the other guy the same way. This is negative 1 over e to the positive infinity squared plus 1. What happens if you square negative infinity like this? So here's my like shorthand for this, my way of making limits at infinity easier. In your mind, replace the word infinity with unimaginably large number, or just really big number. If you take a negative really big number and you square it, what do you get? You get a positive really big number. So this negative on the outside of the parentheses is what moved my guy downstairs. And then once he's downstairs, negative big number squared is positive big number. So this is 1/2 negative 1 plus 1 over e to the infinity plus 1/2 negative 1 over e to the infinity, because here again, positive big number squared is positive big number. And e to the infinity is infinity. Think about the graph of e to the x. So this is 1/2 negative 1 plus 1 over infinity plus 1/2 negative 1 over infinity plus 1. All right, so what is 1 over infinity? What happens if you take 1 and you divide it by a very big number? Yeah, you get something very, very small, right? So that limit is 0. This is 1/2 negative 1 plus 0 plus 1/2 negative 0 plus 1. So this is negative 1/2 plus positive 1/2. The whole thing is 0. So what's true of my integral? Is my integral convergent or divergent? Yeah, very good. The integral converges, or we would say it is a convergent integral. Thus, the integral negative infinity to infinity x e to the negative x squared dx converges. And has value 0. Okay. So this is how we handle bilateral integrals. Integrals from negative to infinity are done this way. The other thing I'd like to address today is how to handle type 2 integrals where the problem spot is in the middle. Do you know what I mean by that? I suppose first, any questions on what we've done here? Questions on this problem? Try to kind of zoom out. It's not all going to fit in one thing. So let's do it like this. Any questions up to here? How we split the integral, why we set it up like this, the antiderivative step. Questions on any of that stuff? Any questions on the steps after the substitution? Okay. Moving on from here. That's what happens when you have a type 1 integral that's got problems on both sides. What about type 2 integrals with problems on both sides? In other words, how do we handle type 2 integrals where the infinite discontinuity isn't at the end point? For example, integral -1 to 1 of 1 over, let's say, x to the, shit, what do I need to do here? 2/3 dx. Can everybody see that this integral is improper? The graph of x to the 2/3, 1 over x to the 2/3 looks like this. So there's this vertical asymptote at x equals 0. Yeah, and 0 is in between -1 and 1. I'm trying to integrate from here to here. So not only do I have this problem where I'm approaching 0 on the left, and that might be infinite, I also have this problem where I'm approaching 0 on the right, and that might be infinite. And we saw 2 integrals like this on Wednesday, but in both of those integrals, I was going from 0 to 1 rather than from -1 to 1. So kind of just like our bilateral integrals, we split it up into 2 integrals that are like the ones we saw on Wednesday. Here, we're going to split this up into 2 integrals that are like the ones we saw on Wednesday. Like this. You can see how this might become tricky. If you don't even notice that the integral is improper, you're in real trouble. It's possible to completely miss the point on these. So please be careful. In other words, drawing this picture is usually a really good idea. All right, so kind of following the same sort of ethos that we did in the previous problem, the idea here is to treat each of these guys completely independent of one another. So this first guy gets treated as the limit as r goes to 0. I'm going from -1 to 0, so r here is going to sneak up on 0 from the left. Integral -1 to r, and then 1 over x to the 2/3 dx. And the other guy gets treated as limit, I have to use a different variable again, limit as s goes to 0 from the right. So I think about s coming in from this side. Integral s to 1 and 1 over x to the 2/3. So it's very similar to the bilateral integral. And then each of those is a power rule problem. So I'll continue down here. This is lim r to 0 minus integral -1 to r x to the -2/3 dx plus lim s to 0 plus integral s to 1 x to the -2/3 dx. I'll add 1 to the power and divide by that new power. The result, the antiderivative looks the same in each piece. -2/3 plus 1 is +1/3. So this will be lim r to 0 minus 3x to the 1/3 evaluated from -1 to r plus lim s to 0 minus 3x to the 1/3 evaluated from s to 1. The 3 is coming from dividing by 1/3, right? We add 1 to the power, -2/3 plus 1 is +1/3, and then we divide by that new power. Dividing by 1/3 is the same as multiplying by 3. So I'm just doing my power rule there and kind of simplifying it a little bit in one step. Any questions so far? Like, could I swap the role of R here and the role of S here? Is that what we're asking, James? Like, does it matter which one I choose? Nope, doesn't matter. And you could use like T and Q or whatever letters you want. Doesn't have to be R and S. I think the book uses a little t, but I prefer this notation because it connects better to what we're going to do with series. But no, it does not matter. Up to you entirely. I think the usual guidance that mathematicians use is introduce new variables in alphabetical order. So I use R first because it comes first in the alphabet. But yeah, it does not matter. Any other questions up to here? I'm not 100% sure what you're asking there, Nick. Could you be a little more specific? So it's the vertical asymptote here that's giving us the problem, right? Rather than a horizontal asymptote. So I'm not sure I understand the question. Oh, well, yeah, then that would be a type 1 integral, right? So if we were integrating from 0 to infinity or 1 to infinity, then yes, that would be something that we'd have to set up like the problem we just did. So I think I understand now. Are we asking like, what if we've got a vertical asymptote and a horizontal asymptote, and we want to integrate over both of those, kind of? Is that sort of what we're asking? This function does happen to have a horizontal asymptote at y equals 0. So let me see if I could create a situation that's like what you're asking. Like, what if I wanted to do the integral from 0 to infinity of 1 over x to the 2/3? Like, what if I wanted to do an integral that measured all of this? Is that what you're asking? If I had to do something like this, I would split it, because there's a type 2 problem at 0 and a type 1 problem at infinity, I would do this as the integral 0 to 1 plus the integral 1 to infinity. There's an area under the x-axis we had to measure as well. Well, so the things we're integrating here are functions. So I couldn't have a part of the curve being upstairs above the x-axis here and a part of the curve downstairs below the x-axis here. So essentially the idea is to take any more complicated problem of this nature and split it up into ones that are like the guys we saw on Wednesday. So if you had any combination of type 1 and type 2 issues, like a vertical explosion or a horizontal explosion, then you would want to split it into integrals that measure one of those at a time. And if you had two functions, so you had something else going on down here, like this, I'm not, whatever this curve might be, the game would be to handle the above stuff as I've written it out there and handle the below stuff here totally separately and then add them up. Yes, exactly. So if you have any combination of these sort of issues, you split it up into individual ones, each of which is just type 1 or just type 2, and handle those on their own. Okay. No, it's a good question. Actually, you're looking forward into what I'm going to show you next. So the very last thing I'm going to show you from the computational standpoint is how to handle something like that. So it's a great question. All right, let's proceed with the evaluation step here. So I have limit r to 0 minus 3 times r to the 1/3 minus 3 times negative 1 to the 1/3 plus lim s to 0 minus 3 times 1 to the 1/3 minus 3 times s to the 1/3. Sorry, 0 plus here. This limit is 0 plus. Now you see there's so much stuff to keep track of, right? We have to be careful. Now our last move is to take these limits as r goes to 0 from the left, r to the 1/3 goes to 0. Here's the graph y equals x to the 1/3. So as r goes to 0 from the left, I think about wandering in towards 0 here. So this piece is 0. And then negative 1 to the negative 1/3 is negative 1. So that's this first piece, plus 3 times 1 to the 1/3 is just 3. And then I'll have minus 3 times 0, because as s goes to 0 from the right, I think about wandering in here. So I get 3 times 0 plus 3 minus 0, that's 6. So here I would say, because both integrals -1 to 0, 1 over x to the 2/3 dx, and integral 0 to 1, 1 over x to the 2/3 dx converge, so does the integral -1 to 1, 1 over x to the 2/3 dx. Moreover, integral -1 to 1, 1 over x to the 2/3 dx is equal to 6, as value 6. So kind of what you'll notice is that these integrals converge or diverge depending on how their antiderivative behaves at the problem point. For a type 2 integral, if his antiderivative doesn't have a vertical asymptote at 0 or at whatever the problem point is, then the integral will converge. And for a type 1 integral, if his antiderivative doesn't have a problem as you go off to infinity, i.e. has a horizontal asymptote, then the integral will converge. The question of how does a function's antiderivative behave compared to the original function is a tricky question to answer a priori, but we're going to develop some theorems next that will help us with that. Are there any questions on the raw calculation here? So remember the power rule. You good there? Yeah, -2/3 plus 1 is +1/3. That's all. Sorry, here as the sun rises, I get more light through my window, so I need to adjust the contrast. Yeah, no worries. If I was integrating a square root, then I would have ended up with the 3/2 there, but I'm integrating 1 over the cube root squared. Any other questions? Yeah, no stress. Any other questions on this guy? Are we all comfortable with the limit step at the end? So I'll remind you another, again, a useful fact. Is that the limit as r goes to 0 of r to the p is equal to 0 if p is positive. And that's true for left limits or right limits. This can be a real time saver in passing from like this step. You might go, oh, well, I'm not sure what this is, to this step, right? This is 0 because this power here is positive. If this power was negative, I'd be in real trouble. The integral would diverge because then the limit would not be finite. Okay, I'm going to move on from this. If you want to see the beginning of this problem, please watch the video. I'll upload the video as quickly as I can after class ends. But the idea was that we take this integral who has a problem in the middle and we split it up at that problem point. So then finally, how do we handle, well, what if I mix all these things together? Right, so like type 1, type 2, bilateral, and problem point in the middle. For example, I want to do the integral from -infinity to infinity of something like 1 over x minus 3 squared dx. So there's the bilateral problem. I'm going from -infinity to infinity. That's 2 separate type 1 integrals. And then there's a problem at 3, which is certainly between negative infinity and infinity. I'll draw the graph really quickly. Graph looks like this. And here really I'm asking for all the area. So the area from negative infinity to infinity, and I'm worried about this problem spot here at 3. I'm not going to solve this problem, I'm just going to show you how to set it up. I would treat this as integral negative infinity up to somewhere. I would say maybe I'll split it at 2 and at 4. So I would treat this as integral negative infinity to 2, 1 over x minus 3 squared dx, plus the integral from 2 to 3, 1 over x minus 3 squared dx, plus the integral from 3 to 4, 1 over x minus 3 squared dx, plus the integral from 4 to infinity, 1 over x minus 3 squared dx. So this is the sort of nightmare case here, where you've got a bilateral integral and a type 2 problem in the middle. So the type 2 problem in the middle requires 2 integrals, and the negative infinity to positive infinity thing requires 2 integrals. So altogether you get 4 integrals. Pain in the ass. You won't see a lot of this. You will see some of it. I'm not going to solve this problem. We don't have time to do it. And each one of these is something that we've done today. So you can handle those. And they're not terrifying. It's just a little bit of extra work. As long as you remember how to set it up, you'll be okay. So the trick is sketch the graph of your function. Identify what the region whose area you're trying to discover looks like. If it goes all the way off to the left, that's a limit. If it blows up to infinity on one side, that's a limit. If it blows up to infinity on the other side, that's a limit. If it goes all the way off to the right, that's a limit. So here I would say, I would express this as the limit as q goes to negative infinity, integral q to 2, plus limit as r goes to 3 from the left, integral 2 to 3, plus integral s goes to 3 from the right, integral s to 4, plus limit t goes to positive infinity, integral 4 to t. And then at the end, you'd have 4 limits to take. 1 at negative infinity, 1 at 3 from the left, 1 at 3 from the right, and 1 at positive infinity. I don't want to burn more time on the calculation because the really good stuff are these theorems. Ah, shit. We're going to burn out of time here. All right. So, P integrals. The integral from a to infinity, 1 over x to the p dx shows up a lot. This is the limit as r goes to plus infinity. Here, I'm thinking of a as being a positive number. So this is just type 1. All right, if a was negative, then I would be integrating over the problem spot at 0. I don't want that. If p is equal to 1, then this would come out to a natural log. But if p is equal to any other number, then this would come out to it's negative p, so this is x to the negative p plus 1 over negative p plus 1 evaluated from a to r. If negative p plus 1 is negative, then this will converge, because that means this x is really downstairs. And when you plug in r and send r to infinity, that piece will go to 0. Negative p plus 1 is less than 0 is the same as saying 1 is less than p, or p is bigger than 1. And if negative p plus 1 is greater than or equal to 0, then this integral will diverge. So that's the same as saying that 1 is greater than or equal to p, or p is less than or equal to 1. So integrals of this form are called p integrals. And they converge if and only if p is bigger than 1. That's the take-home message. They're very, very common integrals. They show up a lot. We've done a handful of them by hand ourselves. And the idea is that if p is big enough, then 1 over x to the p will go to 0 fast enough that that area is finite. That's what we need here. So we're integrating from a to infinity, where a is positive. And what we need is for this curve to settle down on the x-axis fast enough. So the larger p is, the faster that function will sit down on the x-axis. And that's what we need to get convergence. We need this height to get small really fast so that the area can be finite. And it turns out that the magical tipping point is 1. So for example, the integral of from 1 to infinity of 1 over the square root of x dx diverges, because it's equal to the integral 1 to infinity 1 over x to the 1/2. And here this is a p integral with p equal to 1/2. The integral 1 to infinity 1 over x to the 3/2 dx converges, because it is a p integral, with p equal to 3/2. So the 1/2 was smaller than 1, and 3/2 is bigger than 1. And that's what our theorem says. Our theorem says that p integrals converge if and only if p is bigger than 1. And diverge if p is less than or equal to 1. Let's see. Yeah, we're going to be real tight on time here. So rather than trying to cram everything else in, what I want to do is help you really understand this. I'll give you a second to write. It's important that you don't try to apply this to integrals which are not p integrals. P integrals are always integrals from a to infinity, meaning they're always just type 1 integrals, no mixture of type 1, type 2, no like nonsense with infinite discontinuities. So just integrals from like 1 to infinity or 5 to infinity or 2 to infinity. And the thing you're integrating has to look exactly like this. Exactly like this. Just 1 over x to some power. All right? Can't be anything else. Can't have any sign of x upstairs. Can't have any other tomfoolery downstairs. Has to be a straight up 1 over a power of x. If it is straight up just 1 over a power of x, and it is just a type 1 integral, then that is a p integral. And you can say whether they converge or diverge immediately based on this theorem. I'd like to show you some pictures. Just 1 or 2 more seconds here for anybody who's still writing. So the examples we have down here is that 1 over the square root of x integrated from 1 to infinity diverges because the square root of x is the same as x to the 1/2. So that is a p integral. And there p is equal to 1/2. 1/2 is not bigger than 1. It's less than 1. So that is a divergent p integral. On the other hand, the integral from 1 to infinity of 1 over x to the 3/2, that's also a p integral because it's just straight up 1 over a power of x, and we're integrating from 1 to infinity. So there's no type 2 stuff going on here, no infinite discontinuities. That's a p integral in which p is larger than 1. Yeah, good question, Zach. So what about the integral from 2 to infinity of 5 over the cube root of x dx? So here I've got a constant in the numerator. Is this a p integral? Not quite. However, it is a constant multiple of a p integral because I can pull the 5 out. And then the cube root of x is a 1/3 power. So if you can rewrite your integral as a p integral, that's okay. Because this 5 can be popped out, that's okay. Because now this is a p integral. So on its own, if I asked you, is this a p integral? The answer is no. I want to be clear about that. This is not a p integral because it doesn't fit that exact form. But it is a constant multiple of a p integral. So this is a constant multiple of a p integral. And the p integral so forget about the 5 for a minute. The 5 is now out front. Does the integral that's left over converge or diverge? Diverges, right? Because 1/3 is not bigger than 1. It's less than or equal to 1. Therefore, our integral diverges, right? So 5 times infinity is still infinity. So while we have to be very, very careful with our language, the integral in question here is not a p integral, but it is a constant multiple of a p integral. So this p integral diverges, therefore the original integral diverges. And we really do have to be that careful with our language. I know it might seem annoying, you might feel silly, but you'll be surprised at the little ways you can make mistakes here. So I want you to be this careful. I really do. And the textbook is like this. The homework problems on WebAssign are like this. They'll have you say things like, this is a constant multiple of a p integral, rather than saying this is a p integral. If this was an x upstairs or something else, sine of x, cosine of x, not a p integral, right? If it was an x upstairs, you could actually combine the x's into a single power. So you could make that work. But if you had something up here that was more complicated than that, you couldn't. So make sure before you ever make a declaration regarding p integrals that the thing you're messing with is actually a p integral. In other words, make sure you can rewrite it like this. The 2 down here isn't a problem. A 3, 4, 5, pi, 7, 10, a million, any of those would be fine. -1, no good. 0, no good. Because then it's also a type 2 integral, because you've got the infinite discontinuity at 0. So there's a lot of little ways that this can get muddied up. Okay. I want to show you a little something in Desmos. Oops, sorry. Can't see what I'm typing. Here we go. Here are the graphs of 1 over x to the n for n equals 1, 2, 3, and 4. I'm going to focus just on quadrant 1 here. In fact, I'm going to focus just to the right of 1. So what you see is that if I start with the red 1 over x and then compare it to 1 over x squared, look how much faster the blue function sits down on the x-axis. So the area under the red is much larger than the area under the blue. According to our theorem, the integral of the blue function from 1 to infinity is finite. The integral of the red function is infinite. 1 over x cubed sits down even faster. 1 over x to the 4 sits down even faster. So as long as you're under the red function by a considerable amount, you'll converge. It turns out that the red function is sort of the magical tipping point. If you look at something like 1 over the square root of x, see, he's bigger. Or 1 over x to the 0.9. Whoa, hold up. Right, compare the two red functions. So if p is larger than 1, 1 over x to the p goes to 0 faster than 1 over x. And if p is smaller than 1, then 1 over x to the p goes to 0 more slowly. And the idea here is that the red function 1 over x is sort of this magical tipping point. The integral from 1 to infinity of 1 over x diverges, but anything smaller than him by a meaningful amount, like 1 over x to the 1.1, would converge. So even though these guys are very close, the integral of the red function diverges, the integral of the green function converges. Here p is equal to 1.1, just a tiny bit bigger than 1. Here p is equal to 1. So all of these guys beneath the red, they converge. And anything above the red diverges. And what that's getting at is what's called the comparison theorem. Now, unfortunately, we're out of time for today. So I'm going to have to pick it up here on Monday of next week. That means I will have to give you a little bit more time on the current homework because the current homework does have a little bit more stuff in it that we haven't been able to talk about. But that's okay. This is acceptable. So on Monday, I'll go back through the p-integral argument, and then I'll also show you the comparison theorem in the textbook. Before you leave, I want to ask everybody to do something. I know that you're not used to this in math classes, but I'm going to ask you to read. All right. In your textbook, please read section 7.8. It's a good section. And there's a lot of definitions in here. There's a lot of sort of subtle things that we've talked about. And there are some things that we haven't talked about. Here you see them comparing the 1 over x squared integral with the 1 over x integral. Here you see some examples that we have played with and some examples that we haven't played with. And they talk about p-integrals. And they talk about type 2 integrals. They'll talk about how to combine them. But this is kind of the big deal. The comparison theorem is the thing that I wanted to get to today that we haven't had time to get to, and I'm sorry about that. But I would like you to read the comparison theorem. Attempt the homework problems that have to do with the comparison theorem. You can do all except for like the last 3 homework problems based on what we've discussed this week. And I would encourage you to read this portion of the textbook and attempt those remaining problems because it's fairly intuitive. And this way of thinking is going to be a really big deal for us as we move into the series section. So next Monday, I'll wrap up section 7.8, and then we're going to start talking about sequences. So put on your big boy pants, get ready to work really hard. This is a tough little bit of the class, but as long as you allot the necessary amount of time, read the textbook, work the problems, you'll be okay. All right, I do have my normal office hour this afternoon if you want to come chat. Let's see, is there anything else going on? I don't think so. So that is it. I'll see you guys on Monday.